let us carry out a regression analysis. Analyze, regression, and linear. This is where you will find a regression. And let's click on linear. And as you can see, we'll carry out the same regression analysis we did in class. So first of all, your dependent will be total income, and your independence will be gender and the highest level of schooling. Let's say OK and see what the output will be after we are running this test. Click on output, and here you go. So what we can see is that we have, first of all, 3 tables that you will have to report on. The first table always is a table where you can discuss the R and R square, so the coefficient of determination, and the Pearson's R, the coefficient of correlation. For ANOVA, I will discuss this table later, and then your coefficients. So let's start with the coefficients. When you want to write up this regression line, you know that your constant, your y-intercept, is minus 8,355, and that this is significant, so you can generalize it to the population. What does the information of y-intercept convey? It basically looks at how much your dependent variable will be, given that your independent is 0. So in our case, the independents are 0. So sex and education is taken as 0. And this is, you will be owing someone or the government $8,355 without any education and without taking gender into account. This is what constant shows you. Remember that all these coefficients are expressed in the unit of measurement of the dependent variable, and our dependent is income. Thus, everything is expressed in dollars. So, we discussed the constant. Now, let's move on to the slope for gender and for highest level of schooling. In this case, the slope, when we have a multiple regression, we refer to it as a partial slope, and it tells you by how much does your dependent change with a 1 unit change in your independent, taking or controlling for your other independent. So for sex, we take into account a 1 unit change in your independent, meaning that I go from 1 to 2 when I have coded gender, because if you remember, gender is coded as 1 and 2. Let's just quickly go back and see it so you understand it better. Gender, it will be somewhere here. Sex, so see, a 1 unit change in this variable means that I'm going from the code of 1 to the code of 2. So I'm switching from female to male. So let's go back. When this happens, when there's a 1 unit change, when I go from female to male, my dependent variable is going, or my income is going to increase, because there's a positive number. It's a positive number by $12,838. And this as well is significant. You always have to report that it is significant or not. Controlling for education. So education is not taken into account. Based on the simple fact of looking at gender, your income should increase just based on the fact that you're a male versus a female, right? This is what this number reflects. Highest level of schooling, same story for the partial slope, a 1 unit change in a highest level of schooling. Controlling for gender, so gender is not taken into account, will increase your income by $2,706. Now let's go back and see how highest level of schooling is coded, so we understand why this, what it means that a 1 unit change occurred in my independent. So highest level of schooling, where are you? Here it is. So you can see how it is coded. 1 would mean less than grade 5, 2 is grades 5 to 8. So there are a lot of other categories. So a 1 unit change could, for example, mean that I'm going from 9 to 10, which is university no certificate, to university with a certificate. So this is what a 1 unit change will reflect. If there occurs such a 1 unit change that while sex is controlled for, then income is going to increase by $2,706, and this as well is significant. So simply looking at these two partial slopes and comparing them, we would think that gender has a much bigger impact on income than education. Unfortunately, or fortunately in this case, because gender and highest level of schooling are measured in different unit of measurements. Gender is coded as 1 and 2, it's a nominal variable. Highest level of schooling is coded as an ordinal variable and has a lot of categories. You cannot compare the partial slopes to say anything about which independence effect is stronger. So you will have to go and compare the beta weights, the standardized coefficients, for which both independent variables are standardized to z-scores, and only then can you compare which variables effect is stronger on the dependent. As when we compare it, we can see that the highest level of schooling has a stronger impact on your income than the gender. But both of them are pretty close in value. Okay, so this is where you report on which variable is stronger than the other. Of course, when you have a simple regression, you do not have beta weights. Okay, so let's go back. Now, the coefficient of determination, R square, this is one of the most important measures. It's a priori measure, and it tells you the percentage of variance that is explained in your dependent by your independent. In our case, it's 16.7%. And the question is, what does it mean? Well, for every cell for income, for each cell, we have, I think, 650,000 entries in the census long data set, which I was running right now. Income is different for each respondent, for each individual. Income is changing for each individual. So that is a variance in income, right? Income is varying from cell to cell. Now, how can I explain this? I was assuming that education and gender are the two independent variables that can capture this change and explain this change in the best way. However, my test tells me that only 16.7% of this change is explained, which leaves around 83% unexplained, 100 minus 16.7. So there are a lot of other factors that explain this change in income, which we couldn't capture by our regression line. So in this case, it would make sense to search for a third or fourth variable, independent variable, that would try to capture it, for example, ethnicity or something else. And the R, the Pearson's R, is basically a very simple measure that only tells you that the relationship between your dependent variable and your independence, in this case, is strong. So when this is higher than 0.3, you say that the relationship is strong. When it's lower than 0.3 and higher than 0.1, it is moderate. And then when it's lower than 0.1, is weak. So use basically the same categorization as you have found it for the phi and the Kramers B. And remember that this is a priori measure. This is a totally different story when we move to the coefficient of determination. And it reflects the percentage of variance explained in your dependent by your independence. And this is it. For the ANOVA table, the only thing you have to look at is the significance. So you know that your regression that you wrote up is significant. Thus, it can be generalized to the wider population and used to predict future values for your dependent, for income, knowing only the values of your independents. And this is the end of regression analysis.